In this video, we are going to talk about Grosvenor bases. In the first part A, we are going to talk about Buchberger's algorithm, and I want to show you what happens inside and what happens outside of Buchberger's algorithm. What's the output? What's a Grosvenor basis looks like? So we start from a random example. So I use the greplex, which is the ordering that CoCoA chooses by default if you don't specify any ordering. And I write 3 polynomials, and I make a list of these 3 polynomials, and then I compute the reduced Grosvenor basis. This is the output of the function, and we just look at the shape right now. So we see that the leading power products are pretty small, of degree 3. They're all degree 3 in this case. This term ordering, the greplex, is good for computing the homogenization of polynomials because it keeps the degrees low. Usually, that's what happens. If I compute the same, for the same ideal, I compute a lexicographic Grosvenor basis. I need to do in CoCoA a new ring with a lexicographic ordering, because the ordering in CoCoA is strictly related with the ring. Then I compute the reduced Grosvenor basis of, you see, a strange new function, which is bring in. I bring in Q of XYZ with the lex ordering in this ring. I bring in the list L that I define in another ordering. So this is a special way of making a homomorphism. Is a nice shortcut. The code for doing it is horrible, but it is a function which creates the homomorphism, which actually keeps the names of the variables. So if I have X, Y, and Z, they go to X, Y, and Z in the new ring. And if I write here the polynomial ring Z, Y, and X, this bring in just keeps the name of the functions, so they can really do lots of experiments with changing the way I sort the variables as well. So what happens when I compute these Grosvenor bases? I look at the reduced Grosvenor basis, and this is the result. You see the shape of this Grosvenor basis is really quite different. Here I have only 3 polynomials, but then I have that one polynomial has degree 9. So the degree is very high. So the cost of making this choice is that I get fewer polynomials, but much higher degrees, and I have bigger coefficients. Here I see that I have this coefficient, which is, okay, not that big, but you get an idea that when computing in lex, I can have bigger denominators. We will see some big coefficients later on in this video. So now what happens inside a Grosvenor basis? In this computation, because it's so nice, I ask CoCoA to do it, but we are trying to understand what happens inside an algorithm. So we, in last lecture, we show how to implement the division algorithm so that we can know how many steps we do. And we appreciate that CoCoA does all those computations for us. So what happens inside the Grosvenor basis? We talked about the verbosity, and in CoCoA, the verbosity for Grosvenor basis starts from 100, so that we are sure that it doesn't kick in for lower numbers. And this says that CoCoA is doing is finding a new polynomial, adding it to the Grosvenor basis, and it tells me how many polynomials I have in the Grosvenor basis and how many pairs I still have to process. We are going to see the details in a moment. So we want to know more than this, because we are still simulated that we want to write our own algorithm and we want to see inside all the details. So now we implement our own version of Buchberger's algorithm to compute a Grosvenor basis. And we insert the verbosity which does the printout for the progress information. So the first function that we need is the S polynomial, which does this. We have two polynomials. One has the leading monomial x times y. The other one has the leading monomial 2 times a squared. In Latin language, and I'm Italian, LM, the monomial has the coefficient as well. So in CoCoA, which is Latin, we have LM having the coefficients as well. So the least common multiple of the power products, the leading power products, is x squared y. So what we want to do is to multiply G1 by something and G2 by something so that we add them up. The leading monomials disappear, annihilate. So what do? We multiply G1 by x and we multiply G2 by minus y divided by 2. And so the two leading monomial are the same with the opposite sign. So we obtain a new polynomial with a different power product, leading power product, which is minus, which is x times z. So now we write the function for doing this. So we compute the leading least common multiple of the leading power products. And then we multiply G by M divided by the leading monomial of G, which in the example is X. And then we subtract. S originally was for subtraction. So we subtract G2 multiplied by M divided by the leading monomial of H. So in this case, x squared y divided by 2 times s squared. So it is y divided by 2 in the example. And we return this polynomial. So this is our function. We test our function on the two polynomials, and we got the same answer. Of course, we made a good implementation. Now we are about to write our own version of the Buchberger's algorithm. So I want to recall you some of the functions that we need on creating lists and dealing with lists. So I wrote a little handbook for you. So first of all, constructors. If I write L gets square bracket, this is the empty list. And if I write n in 1 to 9 is prime n, it means that it creates, so this is the empty list. This is the list of the numbers from 1 to 9 such that n is prime. This is very similar to the notation we use in mathematics. And indeed, these are the prime numbers between 1 and 9. Or this is something that we're going to use very soon. We create the list of pairs I, 7 with I from 1 to 6. And so we have 1, 7 to 7, 3, 7, and so on. This is the way of creating all the pairs I, 7 with I between 1 and 6. If we want to add elements to a list, we can do in two different ways. One is concatenating the two lists, and CoCoA 5 lets us put together list objects of very different nature. So in this case, we have 4 numbers and 6 pairs. So we create this big set list ordered. Another way, so concatenates two lists and returns a new list, which is the concatenation of the two, and leaves L1 and L2 unchanged. So it is a call by value, is we say in programming. And another function is append. Append modifies the list L1, so it is a call by reference, modify the list L1 and adds one element, which is the element hello, a string. So it returns nothing. So if I call append, it doesn't return anything at all. But the list L1 is modified. And so if I ask to print L1, I see that L1 now contains a 5th element, which is the string hello. When I want to remove elements from a list, I can use the function tail, which takes all the elements except from the head, which is the first element. And we also have the function remove, which modifies the list L. So if I say I want to remove the 3rd element from L1, I call this function, and indeed we have lost the 3rd element, which yes, here it was 1, 2, 3, 4. Indeed, we lost the 3rd. The 3rd element. 3rd element. We lost the 5. Okay, sorry about that. So, end of the little handbook for lists. Now let's see the version of the Grosvenor basis algorithm. So here it is. It is quite short. Oops. So it is quite short. What do? We have I called it silent because then we are making the verbose version, but adding the verbosity makes the add some clutter and it's less easy to read. So I show you the algorithm in this silent version. So at the beginning, we initialize the Grosvenor basis as an empty list and the pairs as an empty list. And then we start with a little cleaning on the generators of the ideal I. So for each F in the list of the generators of I compute the normal remainder, NR, of F by the Grosvenor basis, which at the beginning is empty. And if the result is different from 0, if it is 0, okay, we go to the next one. If it is different from 0, then we append this new element to the Grosvenor basis. And so in the first round, we have one element. And then we add all the pairs I can do with the previous elements. So say that we are adding the 5th element, then we add all the pairs n5 for n, which going from 1 to 4, as we saw in the example before. So we first do this cleaning up of the generators so that we remove if there are any duplicates or if there is some 0 elements or if there are some polynomials which can be reduced before starting the computation. At this point, we have a Grosvenor basis with the cleaned up generators and the pairs that we need to process. Then we start taking one pair, computing the S polynomial, and then let's see it. We take one pair, the first pair, we remove this pair from the list of pairs. We do it in this way. So pairs now is the tail of the list of pairs. Then we computed the S polynomial, which comes from this pair, and we call it G. So then we compute the normal remainder of this polynomial. At this point, I can get that the remainder is 0, and then I do nothing, or the remainder is different from 0. If it is different from 0, I add this polynomial to the Grosvenor basis that we're constructing, and I use append, and I add all the pairs which I can make with this new element. So I add all the pairs and length of GB, which is the index of my latest polynomial G, with then going from 1 to the length of the list -1. And I do this, I repeat doing this until the list of pairs to be processed is empty. And this, we know, the mathematics tells us that this will end at some point because we are working in a Noetherian ring. So it is very, very strong mathematical criterion that tells us that this is actually an algorithm which terminates. At the end, when it terminates, what we have in the list GB is the Grosvenor basis, and we return GB. So this is the silent version, but we want to investigate what happens inside. So I show you where I put the printing. So in the first line, I say that if the verbosity level is bigger than 0, then I write a string which is called my GBases, so that I can print this string at the beginning of each call. Then here I add a line here. So after doing the initialization steps, if the verbosity is bigger or equal to 8, then I ask CoCoA to say that the starting Grosvenor basis is GB and the starting list of pairs is pairs. Then I do all the computations, and what do? I print out here when I choose when I pick the first pair, at the level of the verbosity level 5, I print out that I'm doing such pair, so that I know what polynomials at what point I am. Then I compute I use this function if I want to have all the verbosity of the normal remainder that we did in the last lecture, and then maybe I should go and recollect it because I started new CoCoA before starting this recording. Or if I don't care about the verbosity inside the normal remainder, I just called NR, which is silent and implemented in CoCoA. Then at this point, when I have a polynomial that doesn't reduce to 0, and I add this polynomial to the list, then I ask CoCoA to say, I have a new polynomial, and the length of the pairs to be processed is such and such, is length of pairs. I should pick the previous lecture, 2000. Okay, division algorithm, and I pick the code that I need, which is the reducer index function and the normal remainder. Okay, switch back to this one. So now I read the function myGBases. Okay, so now let's see what happens inside. I call level verbosity 9. I pick my 3 polynomials, which I wrote before, and I call my verbose function. And we see how horrible it would have been to compute this by hand. For example, I want to show you one thing, which is really scary, is that this polynomial, you see, from the pair 6, 8, this is what the division algorithm had to do. Okay, this is horrible, isn't it? So this is all the reduction of this polynomial coming from the S polynomial of the pair 6 and 8. Let's go back to our code. We take the verbosity to 8, so it prints a little less. And we computed the same Grosvenor basis. I didn't write this. So this is the Grosvenor basis at the end. One further step we can do is to introduce this Grosvenor basis. That is, I check all the polynomials and do all the reduction of each polynomial with all the others. And what I get is this Grosvenor basis. You see, it's a little different from what we did before. From what we got before. We have all the polynomials now are monic, and I have some smaller polynomials or smaller leading power product. We are going to see some more striking examples than this in a second. So we do the same computation with Lex ordering. So we compute the Grosvenor basis, and here we see how many pairs we are processing. And we show was the Grosvenor basis we computed, and then we compute the interreduction and make all the polynomials monic. And we see that we have computed a biggish Grosvenor basis when effectively what the real result is just made of these 3 polynomials. So when running a Grosvenor basis computation, we are actually using a lot of useless polynomials, which at the end we throw away. So I show you this very innocent looking example in the Grevlex, and I add some timing to the computation so that we see how long it takes. So this is T0. CPU time is the time in this moment as a CPU time in this moment, so not the clock time, but the CPU time inside the computer as a rational number. So later on, I ask time from T0, which is the same as saying this CPU time at this second moment minus T0 that we said before. And we print it out as a decimal instead of a rational number. Okay, so it took, in CPU time, it took half a second. And this is, this is the result. And you see here that we start having some bigger coefficients. This was with the Grevlex. Now we see the same ideal with lax ordering. This is terrible. This is terrible. This is what happens when you compute with the lexicographic ordering. Usually the computation takes a lot longer, and you see it took 8 seconds instead of half a second. This is the Grosvenor basis. And here you see that the coefficients are a lot bigger when I compute with the lex. This is the length of the Grosvenor basis. And again, I compute the reduced Grosvenor basis. I do the interreduction. And this is the reduced Grosvenor basis. The leading power products of these Grosvenor bases are 3. Z to the 20th power, Y and Z. So it is only 3 polynomials. Whereas the Grosvenor basis we computed at 45. This is what happens inside the computation. Actually, this is outside the computation. Outside the computation of the algorithm, I get 45 polynomials. And when I introduce them, I get only 3, which are the real Grosvenor basis, the reduced Grosvenor basis. An interesting trick is that when a computation takes too long, and that happens very often with Grosvenor basis, I can try to see the shape of a Grosvenor basis. I can try to do the computation modulo a prime number. So let's try modulo 13. So I do the same computation. You see that the steps look a bit the same as before, but instead of taking 8 seconds, it takes 4 seconds. And this is the Grosvenor basis, which is modulo 13. So the coefficients are very small in this case. And the reduced Grosvenor basis, I made something wrong. Introduced of GB13. The reduced Grosvenor basis is this, and you can notice that the leading power product in this Grosvenor basis are the same as in the computation over the rational numbers. So sometimes it is enough when you investigate a very hard problem to choose a good prime, and this is a research paper we wrote recently. You choose a good prime, and which is essentially almost all the primes, except from a finite number of primes. And you can get the skeleton right. So you can get the leading power product right for your original computation. So I want to tell you a little bit of what the nice properties of the reduced Grosvenor basis are, apart from being shorter. So the very nice thing is that the reduced Grosvenor basis does not depend on the generators. That means if I take another set of generators for the same ideal, at the end, what I get is the same reduced Grosvenor basis. So it just depends on the ideal and the ordering I chose. So as it does not depend on the generators, I can answer questions like, is this ideal the trivial ideal 1? Because if I see these generators, I cannot really tell if 1 is in this ideal. But if I compute the Grosvenor basis, this is it. And the reduced Grosvenor basis is just one polynomial, the constant polynomial 1. So if I start from 1, I get the Grosvenor basis 1. But even if I start from this other set of generators, I do get the same reduced Grosvenor basis. Other questions I can answer with this instrument, the reduced Grosvenor basis, is if two ideals, if an ideal is monomial, because if an ideal is monomial, means that there is a Grobner basis made of monomials, then I do get it with the reduced Grobner basis, because the reduced Grobner basis, if I start from monomials, I get monomials. And if I start from another set of generators, I get the same thing. I get the monomials. So in this first example, this idea, which is not really trivially a monomial ideal, I see that it is indeed a monomial ideal, which is equal to the ideal generated by y, x squared, and z cubed. In these other examples, I compute this is a Grobner basis, this is the reduced Grobner basis, and I see that it is not made of monomials. So this one, for sure, is not a monomial ideal. So I have two exercises for you. So one exercise is that there are some tricks to remove some useless pairs, some pairs which actually will reduce to zero. And you saw how long a reduction can be. So the easiest of these criterion is this one. So the exercise is to modify this implementation that we have so that it prints out the number of all the pairs it processes during the computation. So you just add the counter. Then you modify again so that it skips all the pairs. So instead of computing the S polynomial and the normal reduction of this polynomial, it skips a pair if the leading power products of the two polynomials are coprime. So say one has leading power product x squared and the other one has leading power product yz. They are coprime, so I know that that pair is useless for the computation, so I can skip it. So modify the Grobner basis so that it skips this pairs, and then try to see how many pairs you process in one way and how many pairs you process with this new criterion. Another exercise, I have to tell you a little more for doing this exercise, is trying to see what can go dramatically wrong when computing Grobner basis. I show you this example because, curiously, CoCoA-4, the implementation inside cannot compute this Grobner basis. So don't try, it gets stuck. I will show you a little part of the computation. This is very innocent. We call it the French student's example because it was found by some French students a long time ago. I compute the Grobner basis with my G basis, and then this is the result. So effectively, the same shape as the examples we saw before with just three polynomials, biggish coefficients. So what do you notice about this? You should compare with this, which is the Grobner basis, which was actually computed. Now we set the verbosity very high and see what CoCoA does inside. You see, there are only 5 pairs to do, but every time it processes one pair, it creates a new pair, and then processes another pair and produces one pair, and gets stuck in this cycle. So I stop it. To stop it, you just do Ctrl+C, Ctrl+C. Okay, so it stopped. So why do you think that CoCoA takes this long, longer than my GBases, our implementation. Just to have an idea of what can you do in different ways in different implementations of this very basic algorithm. But just so that you don't lose your faith in a CoCoA, I'll show you that there is another interesting trick. So I told you that you can try with FP with a modular prime, or you can try, and then you get the computation modular prime. But you can also try computing by homogenizing. What does it mean? I homogenize all the input, compute the Grosvenor basis, and then dehomogenize the input, the output. And then what I get is this Grosvenor basis, which is the same that we computed with our algorithm. And that was really fast. Did you notice? So homogenizing is often, but not always, unfortunately, a good trick to compute Grosvenor basis. So I wanted to show you the internal steps for homogenizing and dehomogenizing, because it is something that you might want to do in your own projects. So what we do first of all is to create a ring which has a new extra variable. Sorry for this printouts. These are my own debugging printouts. So this is the ring, and then I need to add this variable for homogenizing, which is h. I call it h, a nice name, and I put deglex as an ordering. So I need to add a degree compatible ordering which is associated to lex. Now I write the two homomorphisms. So if I go from q of xyz to q of xyz and h, and I send the variables x, y, and z in x, y, and z in the codomain. For coming back, instead, I go from xyzh to xyz. So I have to define the images for the four variables, and they send x in x, y in y, z in z, and h in 1. So maybe I should read it. I read it. Okay, so the homogenized generators are these. So I take the generators from I homogenize them with h. So you see, here I had a -1, which is now h to the 5th power, so that this polynomial is homogeneous of degree 5. This polynomial is homogeneous of degree 7, and this polynomial is again a polynomial homogeneous of degree 5. Now I compute the reduced Grosvenor basis of this, and you see it is very fast. This is the result with the h. You see, we have h to the 20th power in this computation. And then we apply the homomorphism to come back to x, y, and z. So I set h equal to 1. And this is it. Okay, reduced of, sorry, I should have written this one. And I think I have one parenthesis too many. Okay, this is correct. And this is the result of, I see, there's some verbosity in the function introduced. And I have the result that I showed you before, 3 polynomials in the reduced Grosvenor basis. So is this the same that was computed before? It should be. Okay, now stop this video now, and in next video we'll see the Grosvenor basis applied to solving polynomial systems. See you later. Bye-bye.